So continuing on our theme of principles, in this video we're going to be talking about layering. So I'm going to start with an example. So layering allows us to decompose a more complex function into a set of simple stages, well-defined stages, with a well-defined API between them that allows us to break down a more complex communication into a series of simpler operations. So imagine that you're doing a file transfer between two endpoints, between, say, a computer over here A and a computer over here B, and we want to transfer a file correctly from one side to the other. What we could do is to, in one great big mass of code, create all of the things that we need in order to perform that transfer. So we start by doing all of the addressing, figuring out where the other end is, establishing a connection with it, making sure everything is in the right format, sending the whole file over, figuring out what we do when things are missing. But layering allows us to reuse bits that people have already created in the past so that we can break this down into bits that we can use, bits that we write that are specially for the particular application. So in the case of a file transfer, we have a file, which might be a sequence of a whole load of bytes at one end that are in a particular format. It could be an ASCII or binary file. And we're looking to reproduce that whole thing, that whole content at the other end. So we're going to take advantage of the stages that are and the layers that are provided for us already. So for example, we want to make sure that the things that go across are in the correct format. I'm going to say that they're in ASCII in this particular case. But I also want it to be delivered in packets because I want to take advantage of the fact that there's an internet sitting there. So I've somehow got to go from this file down into the packets. But I also want to make sure that those packets are reliably resent if any of them are missing or any of them become corrupted along the way. I also want to make sure that they're put down in the format on the wire that can be used on that first link. So they need to be using the right electrical signals, they need to be using the right packet formats. So all of these things that we have to get right, many of them are common to many, many applications. So we normally think of an application as having many different layers, many of which are common to different applications. So in this case, I've got the data format, that's telling me the format of the data that I'm using. Packetization, which is breaking it up into the packets of information that I'm going to use to send to the other end. Reliability and error checking, meaning I'm going to check that each one of them is correctly delivered, and then fill in or retransmit any that are missing. I'm going to perform flow control to prevent the other end from being overrun, and perform congestion control in the network. Each individual packet will be delivered and routed through the network by starting out over the first link to the first router and using the correct signal modulation and framing layers. So now let's take a deeper look into this idea of layering.
So as Nick was saying, any complex protocol has a wide range of things it needs to accomplish, from reliability to routing to data formats, etc. And so the whole idea of layering is that we want to take this somewhat complex process of communication and break it up into a set of smaller, well-defined components. And because these components build on top of one another, for example, if I can modulate the signal on the wire, then I can send a link layer frame over the wire, which then allows me to route packets over multiple wires. Because these building blocks build on top of one another, they're called layers, and sort of the terminology of they layer on top of one another. And so what's really important is that each layer has a well-defined interface, that is how you interact with it, as well as clear responsibilities. So for example, a routing layer is responsible for delivering a packet from one node to another node across multiple hops. It doesn't at all care about what the application level payload of those packets are. It just wants to take packets of data and deliver them to an endpoint. That's the routing layer's responsibility. Similarly, or conversely, the application layer doesn't at all care about how the signals are being modulated on the wire. It doesn't care about voltage levels, it doesn't care about modulation. It just wants to put application data in and have application data appear at the other side. And so these two concerns, these two pieces of functionality are separated. And one of the real benefits of this is really a system design principle, is that each of these layers can evolve independently. So even as we get new versions of Wi-Fi, 802.11a, B, G, N, AC, all the applications we have still continue to work unchanged. Similarly, whether or not you're plugged into a wired Ethernet or wireless, your application continues to work unchanged. Even if we were to change make some changes to HTTP, that's not going to change how TCP, which provides reliable communication between applications, works. TCP will remain unchanged. The application can change independently of it. And so there's this whole idea of taking what might be a complex, multi-component problem and breaking it into very simple parts with clear interfaces. So let's look at one concrete example of this layering. So we're going to look at 3 different layers called the transport, network, and link layers. And so the transport layer is what we normally think of as the end-to-end transport between applications running on hosts. So for example, when your web browser connects to a web server, it's using a transport layer, say TCP. And so it's responsible for reliability, congestion control, flow control, and has a bunch of other responsibilities. However, TCP is not responsible for figuring out how to get any given packet from A to B. That's the network layer's job. This is where the network layer is what routes data, routes packets. So given some destination address, the network layer is what takes that packet and decides which of n possible links it should take in order to get towards the desired destination. Now the network layer, in order to traverse these many links to get from the source to the destination, has to use the link layer. And the link layer is responsible for actually getting a packet across a single link. And this involves the kind of link that it is. Is it wireless? Is it wired? But the network layer doesn't care. It just knows it has the link. It has a link it's going to use, and it just sends the packet over that. And so each of these has an interface. So the transport layer is using the network layer's interface, which is deliver a packet across network. Meanwhile, the network is using an interface of the link, which is deliver packet across link. Now, the link layer doesn't care about multiple hops, nor does it care about reliability at the end-to-end or congestion control, nor does the network layer care about flow control. And so the point being that by separating these concerns, we can have TCP optimize its tasks and do its job as well as it can, independently of how the network layer works and accomplishes its task, independently of how the link layer works and accomplishes its task.
So back in the 1980s, it seemed worthwhile to try and standardize some of these interfaces between these layers to have a common understanding of what the different layers would perform, because they're so commonly used in many applications. So there was a standard model that was created by the International Standards Organization called the OSI model. And the OSI model, standing for Open Systems Interconnect, was defined as 7 layers that would be commonly used, such that we could replace any one of these layers as a new implementation of that layer was performed, perhaps providing different specific implementations, but providing the same general services. So this particular 7 layers starts at the bottom with the physical layer, and the physical layer is really referring to the way that bits and bytes are put onto the wire, voltage levels, optical signal levels, the size of connectors, that kind of thing. The next one is the link layer, and this is the first framing format. So in an Ethernet frame, then this would be an example of the link layer with its header and its data operating at the Ethernet layer. And then the network layer is that layer which is delivering datagrams from one end to another. We would now today think of that as IP, although IP wasn't really around very much in the times that this was defined, with its own header and data format, which of course then becomes encapsulated into the data portion of the frame below. So now that would commonly be IP for the internet. Transport is what we think of today as the transport layer was captured by the transport and session. The session is the state establishment, the handshake to establish the state at both ends, and then the transport is the reliable delivery of segments from one end to another. Presentation will be the way in which that data is delivered, its format, whether it's encrypted, the security model that's being used, and then the application will be the application level protocol, whether that's like for email, which would be the SMTP, or for the web, which would be HTTP. It's the protocol that they're using to exchange information about the application from one end to the other. This 7-layer model was a nice way of capturing this layering structure and is very widely referred to. You'll have seen in another video us talking about the 4-layer model that's used in the internet. That's collapsed some of these layers. They all provide the same functionality, but it's proved a more useful categorization in terms of the internet. So in each of these layers, there is a well-defined service model or a well-defined interface between each. So they are providing a service to the one above. So for example, the network layer is saying to the transport layer, if you deliver datagrams of information or information that I can put into a datagram, I will, with best effort, deliver it to the other end. And so each one in turn is offering that well-defined service to the layer above, allowing the layer above not to worry about the implementation of things that sit below it.
So as Nick was saying, the internet, the 4-layer internet model, is a little simpler, and in some ways it's a bit easier to handle, because essentially what the 4-layer internet model does is merge these top 3 layers, application, presentation, and session, into one layer, and merge the link and physical layers into one layer. Because from the internet standpoint, the action is at layer 3, that's the narrow waist, and then there's transport, and then all the stuff above it. And so generally speaking, what Nick was saying is right, is that while the layers 1, 2, 3, and 4 tend to be very well defined as to what they do, we modulate bits, we put things on a link, we deliver a packet from one host to another, we deliver data from one application to another, the boundaries in layers 5, 6, and 7 are at times a little less clear. And so there can be arguments as to whether something is a presentation layer or a session layer. But generally speaking, it can still be a useful abstraction. For example, transport is TCP. This is a reliable connection between 2 applications. But then there's something called TLS, or Transport Layer Security, which is a security protocol used in, for example, when you do HTTPS, secure web browsing, which sits on top of transport. It's providing transport, but it's actually technically, in terms of the way they discuss the protocol, operating at the session layer because it sets up a secure session. But it's providing a transport layer abstraction. So the distinctions can start to get a little fuzzy once you get above layer 4. But nevertheless, the way I think is these aren't hard and fast boundaries as you go up, but rather a conceptual model that helps you just categorize what a protocol does and understand what its responsibilities should be.
So we can summarize the principles of layering really in 3 main points. First of all, we're decomposing a more complex function into a set of layers of abstraction. And any system that we build that is complicated, it kind of really makes sense to decompose it. We think of this in almost any complex system that we build, whether it's a program or whether it's an entire communication system. But in the context of computer networks, these communication layers are defined so that they separate the concerns so that you can exchange these layers at later times so that they can provide the same abstraction to the layers above while implementing in a different way. But the separation of concerns allows a layer above not to have to worry about the way that layers below have been implemented. And this then allows each layer to evolve independently over time and to be steadily improved. And we've seen some remarkable examples of this in the internet, and you'll be seeing those throughout this course.